Everything that you fundamentally believe you know about the Big Bang is, according to modern physics, profoundly incorrect. And I am certainly not referring to some fringe sensationalist conspiracy theory here. I am talking directly about what actual working physicists currently believe versus the vastly simplified model they taught us when we were in school. Because here is the single staggering fact that is going to entirely blow your mind and shift your entire cosmic perspective. The vast majority of professional physicists today do not believe the Big Bang was the absolute beginning of the universe. Please allow that monumental concept to truly sink in for a necessary second. The Big Bang wasn't the origin. So, what precisely was it then? What in actual fact banged? Was it a singularity? Was it merely nothingness? Was it something entirely different and far more complex? Comment your city name below and tell me, have you noticed anything unusual in the night sky lately? Any distortions? Any flickering of stars that shouldn't flicker? Any sense that something fundamental has shifted? Stay with me for the duration, because by the end of this journey, you are going to grasp a core concept that even most dedicated science teachers get completely wrong due to outdated curricula. If you are captivated by the profound mystery of how the universe truly began and want to see more mind-bending cosmic stories, enthusiastically smash that like button and let the universe know you are watching this revelation. Every single click helps significantly to keep the vital search for the unknown alive. Now, before we deeply dive into what the Big Bang really represents, we need to go back, way back in history. This is because humans have perpetually looked up at the vast starry heavens and wondered about the ultimate source of all this existence. The ancient Greek philosophers widely thought the universe was spatially infinite. The Hindu traditions believed it went through endless, cyclical phases of creation and destruction. And then, in 1687, a 44-year-old brilliant mind named Isaac Newton changed absolutely everything. He published his seminal Principia and brilliantly showed that the same fundamental laws of motion we observe here on Earth apply uniformly everywhere in the cosmos. Gravity as a universal force was profoundly born. But here is where the narrative immediately gets very interesting. Newton quickly encountered a massive inherent problem. If the force of gravity pulls everything together, why doesn't the entire universe just immediately collapse in on itself into a single point? His necessary solution was that the universe must be utterly infinite with no gravitational center, with everything being perfectly, delicately balanced. The concept of the static universe was thus born. It was a universe that never changes, never grows, never shrinks. It just sits there eternally. For over 2 long centuries, almost everyone firmly believed this model. But there was a critical crack in the foundation. A problem so obvious that once you hear it articulated, you will wonder how anyone missed it for so long. When you look up at night, you see stars and you see darkness, right? But if the universe is truly infinite and eternal, like Newton's model proposed, you should be able to look in any direction and eventually see a star or a galaxy. The entire night sky should be uniformly as bright as the surface of the sun. And yet, demonstrably, it is not. Something was profoundly wrong with this picture, a dilemma known as Olber's paradox. Enter the towering figure of Albert Einstein. In 1915, Einstein abruptly drops his revolutionary theory of general relativity and completely turns physics upside down. He discovers that as you speed up, time slows down. Space and time are not separate things. They are inextricably woven together into one unified, flexible fabric called space-time. And gravity, he showed, is not a force pulling things together. It is actually the bending of space-time itself caused by mass and energy. The sun doesn't pull the Earth, it warps the fabric of space, and the Earth simply rolls around this curved surface like a marble on a stretched rubber sheet. Now here is where the story gets truly wild, and I need you to pay extremely close attention because this concept is going to connect to something massive later on in our discussion. In 1919, during a total solar eclipse, scientists conducted a critical test of Einstein's theory. If he was right, the light itself from distant stars should demonstrably bend around the immense mass of the sun. And guess what they discovered? The star's apparent positions shifted during the eclipse, exactly as Einstein had precisely predicted. He became an instant global celebrity. The Times of London famously declared that Newtonian ideas had been unequivocally overthrown. But Einstein immediately ran into the identical problem Newton had faced centuries earlier. His complex equations, derived from general relativity, showed the universe was inherently unstable. It absolutely had to either universally expand or globally collapse. And Einstein, he personally hated that dynamic idea. So he did something quite interesting, though ultimately regrettable. He manually added a concept called the cosmological constant, lambda, to his equations. Basically, he postulated that empty space itself possesses a certain inherent energy. He could then carefully tweak this specific value to keep the universe artificially static and unchanging. He would later call this addition his biggest blunder. But hold that thought very firmly, because we are going to circle back to this concept, and you are going to see why Einstein might have actually been right all along about the energy of empty space. While Einstein was rigorously wrestling with the complexity of his equations, astronomers were making groundbreaking discoveries that would shatter everything we thought we knew about cosmic scale. For centuries, people had observed these fuzzy, indistinct clouds in the night sky. They universally called them nebulae. The most famous one was Andromeda. Nobody knew what they truly were. Were they just insignificant clouds of gas within our own Milky Way galaxy, or were they something much more monumental? A brilliant pioneering woman named Henrietta Swan Leavitt figured out a crucial method to measure the distance to these objects using variable stars. And when Edwin Hubble used her method to precisely measure the distance to Andromeda, his result changed everything forever. At 900,000 light years away, it was impossibly far beyond our own galaxy's boundaries. In that single revolutionary moment, the known universe instantly increased in size by 1,000,000 times its previous estimate. Those fuzzy clouds, they were actually entire galaxies, vast islands of billions of stars, just like our own Milky Way. The universe was suddenly unimaginably bigger than anyone had ever truly dreamed. But Hubble's work was far from finished. He noticed something even more profoundly shocking. Most of these distant galaxies were moving away from us, not just casually drifting, but actively racing away at hundreds of kilometers per second. And here is the essential kicker, known as Hubble's law. The farther away they were situated, the faster they were moving. This is exactly what you would observe if the universe itself was uniformly expanding. The static universe model was irrevocably dead. Einstein's original equations had been correct all along. The universe was fundamentally dynamic, changing, and perpetually growing. Now pause and think about this implication for a second. If the universe is dynamically expanding right now, what physically happens if we digitally rewind the clock? Everything gets closer together, becoming denser, hotter. Keep rewinding, and you ultimately arrive at a singular point where everything in the universe, all the matter, all the energy, and all of space itself is compressed into an incredibly, extremely dense state. A Catholic priest and physicist named Georges Lemaitre called it the primeval atom. He famously said, "We are living in the smoke and ashes of a very rapid fireworks display." And because space and time are fundamentally linked, this wasn't just the beginning of space. It was the beginning of time itself, a day without yesterday. This is most likely the standard narrative you learned in school. The Big Bang started from a singularity, an infinitely dense point where all the known laws of physics dramatically break down. Physicists like Stephen Hawking and Roger Penrose even rigorously proved mathematically that this singularity must have existed under the assumptions of general relativity. Case closed and settled, right? But here is the absolute truth they often don't tell you in school. This singularity concept is almost certainly not true. And we are going to get to the profound reason why in just a moment. But first, we need to truly understand the events that happened after this presumed beginning. Physicists accurately figured out that right after the Big Bang, the universe was so intensely hot that it was basically one gigantic seething nuclear reactor. Protons and neutrons were rapidly snapping together in a process called Big Bang nucleosynthesis, forming the nuclei of the lightest elements, hydrogen and helium atoms. They made a precise theoretical prediction that the resulting elemental composition would be about 75% hydrogen and 25% helium. And when modern astronomers meticulously measured the actual abundance, they were exactly right. But the discoveries didn't stop there. Scientists realized that approximately 380,000 years after the Big Bang event, something absolutely incredible occurred. The universe had cooled down sufficiently enough that electrons could finally permanently attach to atomic nuclei. In that momentous instant, all the intense light that had been perpetually trapped in this hot, opaque plasma soup was suddenly free. It flew out through what became transparent empty space and has been traveling ever since. If we could successfully find this ancient light today, we would literally be looking at a baby picture of the Big Bang itself. The exhilarating hunt was quickly and successfully on. By the 1960s, two scientists at Bell Labs, Arno Penzias and Robert Wilson, were rigorously testing a large radio antenna when they detected a persistent, strange hiss in their data. They tried absolutely everything to eliminate it. They even meticulously cleaned pigeon droppings out of the antenna's feed horn. Nothing worked to remove the noise. And then they realized what they were truly looking at. It was the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. This was light from 13.8 billion years ago, stretched and cooled by the continuous expansion of the universe. They deservedly won the Nobel Prize for their accidental discovery. The Big Bang theory had found its definitive crown jewel of evidence. But here's where the entire story starts to critically fall apart, because there were three massive problems with this otherwise beautiful story. Three fundamental things that made absolutely no physical sense. And this is where we are going to discover what truly happened instead. Okay? The first major problem is called the horizon problem. When scientists meticulously mapped this cosmic background radiation, they found something shocking. The temperature is almost perfectly uniform across the entire sky, an astonishing 2.725 Kelvin everywhere you look. But here is the critical issue. There simply wasn't enough time for the temperature to even out. Even traveling at the absolute speed of light, opposite sides of the universe in the standard model couldn't have gravitationally or thermally communicated with each other in just 380,000 years. It should have taken many trillions of years. So how is the temperature so incredibly uniform? The second problem is the flatness problem. Space can be geometrically curved in different ways. It can be flat, where parallel lines stay parallel forever. It can curve inward positive curvature, where parallel lines eventually converge. Or it can curve outward negative curvature, where parallel lines diverge. When we precisely measure the curvature of our universe today, it is almost perfectly flat. But here is what makes this fact insane. A flat, expanding universe is incredibly unstable. It is physically like balancing a sharp pencil on its tip. The slightest deviation early on, and it should rapidly diverge, either violently tearing the universe apart or causing an immediate collapse. So why is our universe so perfectly, precariously flat? The third problem is the monopole problem. At the extremely high energies present in the very early universe, particle physics predicts that huge numbers of exotic, massive particles called magnetic monopoles should have formed. These are hypothetical magnets with only a single pole, either north or south with no opposite pole. The critical problem is that we have never found a single one in nature. And if they had existed in the predicted numbers, they would be so heavy that they would have prevented the universe from expanding at all. Beyond all these immense theoretical problems, there was still the problematic singularity itself. Most physicists felt deeply that something was physically off. Einstein himself famously called the idea that the universe started at a singularity repugnant to reason. The mathematics of general relativity seemed to be pointing to something that couldn't actually be physically real. This is the exact point where a brilliant forward-thinking physicist named Alan Guth enters the story. And what he discovered is going to completely and irrevocably change everything you think you know about the Big Bang event. Guth was conceptually thinking about phase transitions, like when ice melts into water or water boils into steam. But there are also strange non-equilibrium phase transitions too. For example, pure water can be cooled below the freezing point without immediately turning to ice. This is called supercooling. Guth started thinking, what if the early universe went through a similar delayed phase transition? And then he calculated something that made him realize he was onto something absolutely huge. If empty space possesses energy, which quantum mechanics and the uncertainty principle tell us it must, and if this energy drives the rapid expansion of the universe, the rate of growth would be absolutely insane. He calculated that in less than a trillionth of a second, the universe would expand by at least 100 trillion times its initial size. He called this extremely brief period inflation. And here is the magic and the sheer intellectual power of the inflationary model. This period of ultra-rapid inflation immediately and elegantly solved all three of the major problems plaguing the standard Big Bang model. The flatness problem solved. Because no matter what shape the universe started in, this rapid expansion would flatten it out perfectly, just like rapidly inflating a balloon causes its surface to appear flatter and flatter as it grows larger. The horizon problem solved. Because regions that seemed too far apart to have thermally communicated were actually very close together before inflation occurred. They had plenty of time to reach the same uniform temperature. The monopole problem solved. The massive monopoles simply don't get created in the predicted numbers during the supercooled, high-energy phase transition. But inflation did something even more incredible and deeply significant. Remember those incredibly tiny variations in temperature we observe in the cosmic microwave background, those slightly hotter and cooler spots? Inflation explains where those came from. Quantum fluctuations in the inflating field get frozen into the very fabric of space as it expands. And these tiny microscopic variations are literally the seeds of everything. Gravity slowly pulled matter toward the denser, slightly hotter regions. And over billions of years, these tiny initial ripples grew into galaxies, stars, planets, and ultimately us. If it were not for these quantum fluctuations during inflation, there would be absolutely no structure in the universe at all. No galaxies, no stars, no you, no me. So now we can finally answer the central question. What actually banged during the Big Bang? We start not with a singularity, but with utterly empty space. No matter, no light, nothing. But this empty space is pervaded by an underlying quantum field, the inflation field. This field causes a tiny patch of space, something the size of a grain of rice, to grow bigger than our entire observable universe in less than 10 seconds. And here is the essential key realization. At this point, there is still nothing but rapidly expanding empty space. And then inflation abruptly ends, and bang! All of the immense energy stored in this inflation field instantly converts into matter and radiation. This is the hot, incredibly dense Big Bang you learned about in school, the cosmic microwave background, the nuclear reactor that formed hydrogen and helium. All of it comes from the vacuum energy of empty space in that single transformative moment. No singularity is needed. The Big Bang wasn't the beginning. It was a rapid, transformative moment when inflation ended, and all that vast vacuum energy became everything we see, touch, and are made of today. But here is the final, mind-blowing part of the modern, widely accepted picture. Inflation, according to the mathematics, doesn't end everywhere at once. It happens randomly in patches. So while inflation might decay into matter and radiation here, creating our universe and our Big Bang, it continues relentlessly inflating outside our universe, spawning potentially infinite numbers of other Big Bang universes. Each one potentially has its own set of physics, its own fundamental constants, and its own unique story. The multiverse is born, and we just happen to be residing inside one of these tiny local bubbles. Okay, this is the most widely accepted and mathematically consistent view among cosmologists today. Decidedly not what you were simplistically taught in school. When I learned this material just a few years ago, the original presentation was often flawed. They sometimes told us inflation happened after the Big Bang, or the singularity was still presented as a fact. There was no mention of the multiverse concept, but science evolves rapidly. New evidence comes in, better theories emerge to solve old paradoxes, and the inflationary Big Bang is currently our best, most robust description of how everything began. Now, does this mean we have all the definitive answers? Absolutely not. Some physicists correctly argue that the theory of inflation is almost too flexible, not easily falsifiable enough. The multiverse concept makes many scientists understandably uncomfortable because we might never be able to test its existence directly. But here is what we know for certain, beyond any reasonable scientific doubt. The hot, dense phase we call the Big Bang definitely happened. Everything in the observable universe used to be incredibly close together and much hotter than it is today. We can literally see the evidence in the cosmic microwave background. That is an established, non-negotiable fact. What caused that hot, dense state? What came before inflation? Those are the deep remaining questions still being actively explored at the frontier of cosmology. Alan Guth himself truthfully said that the Big Bang theory was never actually a theory of the bang. It says nothing about what banged, why it banged, or what happened before it banged. And that is exactly where we stand today. Standing at the very edge of the cosmic unknown, looking back at the moment our universe was profoundly born, understanding more than we ever have, but still chasing the deeper, ultimate mysteries of what started it all in the first place. So the next time someone tells you the Big Bang was the absolute beginning of everything, you will know much better. You will know that the bang wasn't the beginning. It was a miraculous transformation, a unique moment when empty space filled with immense vacuum energy became the physical everything we see, touch, and are intrinsically made of. And that is somehow even more deeply mind-bending than any simple singularity ever could be. Hey, don't stop your exploration here. The universe is literally full of secrets waiting to be uncovered and revealed. Click on the next video and join us as we explore even more astonishing mysteries about the cosmos, from the baffling physics of black holes to the very edge of reality itself.